Okay, the last talk of this session is from Sriraman Tallam, who is a software engineer at Google in Sunnyvale. The floor is all yours.
Yeah, thank you. Hi, good afternoon, and I'm Shri, and I'm going to talk about why and how we build a post-link optimizer called Propeller for warehouse scale applications. I'm going to try and answer 3 questions in this talk. First, why do we need post-link optimizers and what are they? And why don't state-of-the-art post-link optimizers measure up to the challenge? And how we've made Propeller scale. So for the first question, profile-guided optimizations and link time optimizations are used on peak-optimized binaries, and they've given us double-digit performance improvements. However, there's a lot more performance to be had. This is primarily because profile-guided optimization passes suffer from profile imprecision. So as we go down the optimization pipeline, applying code transformations, introducing new control flow paths and blocks, the profiles of these paths are often approximated and a lot of performance is left on the table. A study showed that up to 3% of performance is dropped due to this. And the heat map on the right shows poor code layout, where the y-axis is the instruction address offsets and the x-axis is time. And we can see that the accesses are all over in the instruction address space. Also, profile-guided optimizers cannot do a certain class of optimizations at the binary level. For example, code alignment to do better DSB utilization, interprocedural register spill removal using caller-callee semantics. These things are hard to do with profile-guided optimizers. So introducing post-link optimizers. Post-link optimizers can solve some of the problems that I just described. So before that, let me just quickly define what a post-link optimizer is. Compared to a regular profile-guided optimizer, a post-link optimizer does not recompile the application, but it directly optimizes the binary. An example is recent Meta's Bolt tool, which is a binary optimizer. It basically disassembles the binary and runs some optimizations on the high-level IR, and then rewrites the binary. Binary optimizers apply specific targeted in a subset of optimizations, and they don't do what a traditional compiler does. Code layout being an example, and code layout seems to recover most of the performance that was lost due to this profile imprecision problem that I talked about. Also, post-link optimizers are profile-guided, and since they profile this highly optimized binary, the profiles are very precise and both context and flow sensitive. And post-link optimizers and binary optimizers enable a new class of optimizations. We could now look at code alignment for better DSB utilization, precise insertion of prefetch instructions, etc. So this is all very exciting. So why doesn't the state-of-the-art post-link optimizers measure up to the challenge? To explain why this is the case, I need to talk about the distributed build systems in warehouse scale applications that build warehouse scale applications like the one that we used at Google. With 50,000 plus developers and 3 billion lines of code, the build times for each build is very fast, and it does more than 15 million build actions every day. And a lot of the build artifacts are cached. This includes the intermediate IR. This includes the native object files. And this content-based caching has a 90% hit rate. But to guarantee the performance, there are hard limits that are imposed on the memory requirements of each process. And for this build system, it's 12 gig. It can go up to 24 gig, but 12 gig is the average. The other example is Chromium builds, which impose a limit of 10 gigs per process for thin LTO builds. Technologies like debug fission, which basically separate the debug information and code, was primarily invented to work with such distributed build systems. And another example is thin LTO, which is a scalable version of whole program optimization and link time optimizations. And thin LTO was primarily invented to work with these build systems again. So there's enough precedence for technologies that have been developed just to work with these complicated distributed systems. So what about the post-link optimizers? So we evaluated Bolt on these distributed build systems, and these graphs show the memory requirements for Bolt to build some of our applications, and these are two separate build actions. The blue line is the baseline, and the red line is the one used by Bolt, and as the binary sizes increase, and the binary sizes are large, think half a gig, as the binary sizes increase, Bolt's memory requirements become intractable. So the learnings from our evaluations of Bolt is that single process, multi-threaded designs of optimizers simply don't scale with these large binary sizes. They are not able to take advantage of distributed build systems, and it is extremely difficult to re-engineer these tools to actually distribute these actions. Also, these tools use disassembly and rewrite to optimize binaries. Disassembly is known to be inexact and is very difficult to debug, especially with CISC architectures. Also, these tools are built as standalone binary optimizers, and they re-engineer the toolchain. So there is significant redundancy. For example, Bolt does its own debug info parse and rewriting. It also does call frame information parse and rewriting. And these tools come in downstream, and they're not integrated well with the toolchain. So this is yet another tool to consider when designing new features for ABI and toolchain compatibility. And while we evaluated Bolt, we ran into such issues, like Bolt doesn't honor kernel restartable sequences. So we could not compile binaries which did that. Cryptographic modules were rewritten by Bolt, and they failed startup integrity checks. Bolt binaries couldn't be stripped, and this was a classic case where these binaries were crashing, and there was this huge argument upstream at who is at fault, whether it's ABI or whether it is Bolt. So given this, we felt like we need another system, another post-link optimizer that can work with these large-scale distributed build systems. And this is one of the primary reasons we designed Propeller. So what are the guiding principles for designing Propeller? We decided there is going to be no disassembly, as we've established that disassembly is a problem. Also, distributed actions are the key, and which are the reason for the memory overheads to be really small. So think of compilation as two separate actions. There is this per module action which operates on like a single module, like a CC file, for instance. And these are lightweight actions, and they do not impose any memory overheads. Whereas it's the final link action which brings all of this together and concatenates it to find the logic binary, which is the memory bottleneck. And that's where we need to be careful and not do anything fancy which would blow up the memory requirements. Also, we wanted Propeller to be integrated very well with the toolchain and not be a standalone tool. So the lightweight whole program analysis was the key to achieve this. So the central philosophy of Propeller is that we use relink as opposed to rewrite. I already told you that most of the build artifacts are cached, so we can just directly go back and dip into this cache and extract the IR without having to do any disassembly, so that problem goes away. Then to reduce the overheads of this whole program action, we were inspired by ThinLTO, and we use summary-based analysis, where we collect summaries from all of the modules and then distribute them into each of these modules when actually building each of them. So relinking previously optimized IR after applying post-link transformations, we call these backend actions, can easily be distributed across the various build machines. We also wanted to build Propeller as a new paradigm for post-link optimizations. We've currently shown how we could do code layout, and we are working on other things like interprocedural register allocation and code prefetching. To give you an example of how we did code layout, the key building block for code layout is basic block sections, which we have invented for this. Function sections, which already existed, taught us how to do function layout. It could reorder functions across the address space in any arbitrary manner. So we pushed the boundary, and we've actually implemented basic block sections at a much coarser granularity. With this feature available, the linker can shuffle the basic blocks of a binary, like a pack of cards. So you can cleave a function into n different ways and spray it across in the address space because of this technology, and it's really, really simple to do this. For more details, I urge you to please go and look at the paper. Let me quickly talk about the performance improvements comparing Propeller and Bolt. And this is for code layout. And for all of our warehouse scale benchmarks, Propeller does as well as Bolt in most of the cases. And in some of the cases, Bolt simply didn't optimize the binary for reasons that I've explained earlier, like the kernel restartable sequences, etc. And if you look at the heat map before and after, the top shows the before, the instruction access now is much tighter in a single band, and that improves the iCache and ITLB utilization, which is where the performance speedups come from. If you look at the peak RAM build actions, again, this is the peak RAM for two different build actions. On the left is the traditional linking, and on the right is profile conversion. On the left, we can see that Propeller is very close to the baseline and almost imposes no overhead on the peak RAM for any process. And on the right is for profile conversion, where Bolt is significantly higher than Propeller, again due to disassembly. So I want to conclude with these final thoughts on hardware-software co-design, where I feel like post-link optimizers can play a very, very important role here. For example, last branch record in the performance monitoring unit has been a significant game changer for the way we do profiling. And what other counter information can we use is an open-ended problem. Prefetch and cache line demote instructions can be very useful to improve the iCache utilization. And things like this in the hardware can greatly enhance the power of post-link optimizers. DSB utilization can be further improved by precise alignment using post-link optimizers. In the case of branch prediction, if the hardware can provide more information to the post-link optimizers, we could utilize it, or vice versa, where the compilers can insert hints in branch instructions that branch predictors can exploit. So this is something that I leave as food for thought and open-ended research problem for the community to explore. Thank you.